Assalamu alaikum guys. This is Najmunisha Asha. Today I came to explain you about the periodic trend shown by S&P block elements. That it shows the impact under the unit 1 atomic structure. So let's be more to the chapter now. Of course, we want to see what are the contents, right? So here I'm going to do the introduction about what the periodic trends, how the S and P block elements are shown. And second is the major one, the size of the atom and ions according to the periodic trends. So under the size of the atoms and the ions, there are three things that we are going to study. The first one is the van der Waals radius. Second one is the covalent radius. Third one is the metallic radius. So now we will move on to the introduction. Yes, the many properties of the atoms, which is depends on the electron configuration, right? And how strongly the outer electrons in the atoms are attracted to the nucleus. So this could be explained by Bohm, the Coulomb's law. He said the strength of the interaction between two electrical charges depends on the magnitudes of the charges and the distance between the electrons. So what he's telling is, simply you can say, according to the Coulomb's law, the strength of the interaction, yes, the strength of the interaction, that depends only in two things. The first one is magnitude of charges. Magnitude of charges. And second one, the distance between them. So distance. This is what is second, the distance. So this is what the Coulomb said, how you can classify about the strength of the interaction. Therefore, the attractive forces between an electron and the nucleus. So I will come to that part, which is depends on, okay, the attractive forces between electron and nucleus. That depends on what? The magnitude of the nuclear charge and the average distance between the nucleus and the electron. So this is what the Coulomb said, that the modification, yes, the attractive force. We are talking about what? The attractive force. Right? Between, we are going to speak here what? The between electron and the nucleus. Same thing. What they are telling is the magnitude of nuclear charge. This one. Magnitude of nuclear charge. Right? Magnitude of the nuclear charge. And the second one, the average distance. The average distance between nucleus and electron. This is what they are speaking. So according to that, the force is increasing, right? You have to know the force is increasing as the nuclear charge increases and is decreasing as the electron moves further from the nucleus. So according to this, you can speak about the force also, right? So what the force is telling, yes, the force is increasing, right? Increase, right? If the force is increasing, it's all right, you can say force increases As the nuclear charge increases, right? One. Nuclear charge increases. Right. And the force is decreasing, right? The force decreases as, right, as the electron moves further from nucleus. This is what they are telling. The force decreases as the electron moves from nucleus. This is what the major strength of thing that we are going to see. The Coulomb's law said about what the strength of the interaction, that is depends on the magnitude of the charge and the distance between them. And he said about what the attractive forces between the electron and nucleus. You can classify it what? The magnitude of nuclear charge, the average distance between the nucleus and the electron. Finally, you can explain about what the force, as the force is increases, the nuclear charge decreases, right? And if the force decrease, the electron move further from the nucleus, your force also will be low, right? So let's see, go for the, we will clear all. Yes, I have talked about this charge between these. Yes, the force increase the nuclear charge. Yes, I told. In an atom that containing a large number of electrons, in addition to the attraction of the electron to the nucleus, each electron experiences, this word is very important, repulsion due to proximity of the other electron. Why? The electrons are negative charges. There should be a repulsion in between them. So they will have, if you have the large number of electrons, you will face about what the repulsion problem. Because of this electron repulsion, cancel some of the attraction of the electron to nucleus, so that the electron experiences less attraction than it would be if other electrons were not there. So did you understand? If you have the large number, the number of electrons, the electron will be experienced into what? The electron repulsion. So this kind of the electron repulsion, what it will be do? It will cancel some of the attraction of the electron to nucleus, what we expect as usual manner, right? So because of that, the outer electrons are said to be screened or shielded from the nucleus by the inner electrons close to the nucleus, and this phenomenon termed as screening effect or shielding. Simply, I can say what the nucleus, right, which is shield your outermost, your outer electrons, right, and this is the phenomenon is called what? The screening effect, or you can say the shielding effect. An electron therefore experience a net attraction by the nucleus that is less than it would be in the absence of other electrons. I already said, okay, you understood? The electron therefore experiences the net attraction by the nucleus. It should be the less than what you expect the expenses of the other electrons. So this partially screened nuclear charge is termed as effective nuclear charge certificate. So why we are speaking about the Z effect? Yes, because of this cancel off and outermost electron may be shielded by your inner nucleus and the electron. So what is happening? An electron therefore experiences a net attraction, and that would be less than what you expect the absence of the other electron. Such partially screened nuclear we are calling as what? The effective nuclear charge effect. So this effective nuclear charge always less than the actual nuclear charge what you expect. The actual nuclear charge is Z, The effective nuclear charge is at EWS. So for a valency electron, the most of the shielding is due to the co-electrons, right? Which is closer to your nucleus. Who are the co-electrons? Yes, those are the closest to the nucleus. They are the co-electron. And this is what valence electron, right? This is what we are calling as co-electron, C. And this is what valence electron, right? Okay. And as a result, the greater the number of co-electrons and higher the number of co-share, greater will be the screen. So did you understand? If the co-electrons increases, the attraction will be what increase? That is the, if the co-electron increases, the number of co-shells also increase. Therefore, the screening effect also will be increased because of what the attraction, more attraction. The effective nuclear charge increases from left to right across any period of the periodic table, although the number of co-electrons stays the same across the period, the number of protons increases. So this is very important. The valency electron added to the counterbalance, the increasing the nuclear charge, thus it screens ineffectively. So guys, before go for that, okay, I will explain about this. Okay, right, left to right, along the period, always your Z effect is yes, your Z effect is increased. Because what the number of co-electrons stays the same across the period, even though the number of protons are increasing. Therefore, the Z effect also increasing across the period, right? The valency electron added to the counterbalance, right? If you're using the valency electron, the increasing nuclear charge, it does screens ineffectively. So therefore, that effect is steadily across the period. So did you understand what is happening? If you use the counterbalance, the valency electron also added, the increasing nuclear charge screens ineffectively. So therefore, what will be happen? The Z effect increase across the period. Next, we will go for what? The size of atoms and ions. So according to the quantum mechanical model, atoms do not have sharply defined boundaries. So how can you speak about what the size, the radius, diameters, the distance? How could we explain about those words? Therefore, we can define the atomic size in a several ways based on the system between two atoms in various situations. So let's move on to the first one is the van der Waals radius. So what's the van der Waals radius is telling us? Yes, he refers very clearly. The van der Waals radius refers, right? Always the non-bonding atomic radius. So I can show you. There is a picture, but before that, this is your one. This is another one. So what is, you can see this distance, right? Yes. So this is what we are telling is non-bonding atomic radius. So simply the van der Waals says about what? They are speaking about the non-bonding atomic radius. Half distance of between two equal and non-bonded, right? Half distance of, right? This is your half. Take the pencil. Use another color. Half distance of, right? When you take your one, this is your distance. This is another distance. The van der Waals is explains about what? The half distance, only this distance of what? Between the two non-bonded. between the two non-bonded atoms in their most stable arrangement where the attractive forces are maximum. So I can show you clearly by showing the right. So what is says by the van der Waals radius is the van der Waals radius is non-bonding atomic radius refers to one half. That is very important. That word called one half, right? The word called one half. The distance between two equivalent non-bonded atoms in their most stable arrangement. That is where the attractive force maximum, right? So I will show the picture. Then it should be. So look at this is very clearly visible. Okay, I can use the annotation. Right. So look here. Look at your van der Waals radius. This is what they are talking about is non-bonded. Okay. When I use the non-bonded, can you see these two are non-bonded? There is no any attraction, right? So when you select this, is okay, this is I1, I2. So this is what we are telling is van der Waals distance. So what is called the van der Waals radius? When it is on the maximum attraction, the first half, the one half, it shows about what? The van der Waals radius. Can you see that this clearly shows you about the van der Waals radius? Okay, we can use the pen. Yes, yes. It's clearly shown. Right, the half of the distance. This is what we are calling the van der Waals radius. Right. Okay, and next we will go forward. Covalent radius. Actually, we talk about the van der Waals radius, that is what the non-bonded one. Here, a chemical bond is the attractive interaction between any two adjacent atoms in a molecule. We are talking about the adjacent atom that should be in an attractive manner. The two bonded atoms are closer together than would be in non-bonding collision, what you have seen in van der Waals radius, right? So here you can see there should be attractive, they could be a much more closer. So they would have been forces what such bonding atomic radius for any atom in a molecule is equal to half of the bond distance, the distance between the two bonded atoms. This is very important. The word called radius is what? That half of the distance, the first half or one half of the distance called what? It's a covalent radius. So the bonding atomic radius, also known as the covalent radius, smaller than the non-bonding atomic radius. This is very important. Why we are telling is the bonding atomic radius, the bonding atomic radius you can call as a covalent radius, is smaller than the non-bonding atomic radius. Who are they? The van der Waals radius. Why? The van der Waals radius, they have that is there is no attraction, there is a distance, right? In between that they non-bonded. But when you take covalent radius, they are bonding radius. Therefore, they together, so the distance between the bonding radius always smaller than the non-bonding atomic radius. So let's see this diagram. It clearly explains you. You can see here, right? This is what is showing what the bonding radius. I made a pencil with a different color. So can you see this is what the bonding radius. So this bonding radius, right, we are calling that is covalent distance. The first half of this we are calling as the covalent radius. And can you see, right, this is also showing what the covalent radius. But what about this? This is the van der Waals radius, right? This is half of this, the van der Waals radius. This is non-bonded one. So that's why you can see this is 215, this is 133 picometer. Why? That's why he said is always, right? Your bonding radius less than non-bonding radius. Statement is very important. You should understand the difference. Why this is 215, why this is 133 picometer, right? Okay, thank you. So this is what the explanation of the covalent and van der Waals radius for iodine I2. Next, we will go for what the metallic radius. Here we are going to speak about the metals. Metals atoms in a metallic structure are bonded to each other by metallic bonds. So half of the bond distance between the nuclei of two adjacent metal atom in the metallic structure called as metallic radius. This is simple thing. Look at this diagram. This is what your metal. So the metal on the attraction, right, that is able to form the metallic bond. This half of the metallic, this full we are between two adjacent nuclei, that is metallic diameter. The half is what we are calling metallic radius. So this is for what the metallic radius. So guys, so I am going to finish. So I have finished this introduction of what the periodic rings of S and P block elements, and I have started with the size of atom and sizes. And my next presentation is based on what the periodic frames of the atomic radii and ionic radii. So you will, by using this connectivity, you will understand how the periodic trend shows the major impact on your atomic structure. Thank you very much. We'll see you again. Assalamualaikum warahmatullahi wabarakatuh.